Okay, so we had a plane AB which was inclined at an angle theta to the major principal plane XX, right? So on that plane AB, we have a normal stress sigma and a shear stress tau acting. All right. So what we did next was we considered the soil wedge ABC alone, and considering the equilibrium of stresses in both the horizontal and vertical directions, we found that sigma, which is the normal stress acting on that particular wedge or on that plane AB, was sigma, and the shear stress acting on that plane AB is tau, right? So we found the relation for that based on major and minor principal stress and the angle at which the plane is inclined with the major principal plane. So my major principal stress was sigma 1, minor principal stress was sigma 3, and theta is the angle with which it is inclined with the major principal plane. So AB is inclined by theta, right? So resolving the whole system of the wedge for equilibrium in the horizontal and vertical directions, we found the representations for sigma and tau as shown in this figure, right? So what we did next was we found the Mohr circle. We drew the Mohr circle. So how did we do that? So we drew the x-axis and y-axis, which is representative of the uh, uh, sigma. OX represents the normal stresses acting, and OY represents the shear stresses acting. So what we did was on the axis that represents normal stresses, that is OX, we plotted our major and minor principal stresses, sigma 1 and sigma 3. So sigma 1 is my major principal stress, I plotted that is OD. Then sigma 3 is my minor principal stress, I plot that, OP. Now I have OP and OD. Now what I'm going to do is I'm going to find the radius of this circle, right? I found the radius of this circle. So radius was equal to sigma 1 minus sigma 3 by 2. Suppose sigma 1 is 100 and sigma 3 is 50. So my radius will be 25, correct? So this is my radius FD, or PF is my radius, that is 25, correct? If this is 100, this is 50, and this is 25 now, correct? Now I will keeping F as the center with that radius, what I will do is I will construct a circle which I call the Mohr circle, which this graphical method was devised by Mohr in 1882, as we discussed in the last class. So now I have this circle, right? This circle represents the system of stresses, right? Now if I draw from the point P, the point O is called the origin, point P is called the pole, okay? So from the point P, if I draw a plane inclined at an angle, any angle, let us call it theta as of now. So if I draw a line PQ inclined at an angle theta, then the point Q, or the when you draw that plane, that line is going to intersect the Mohr circle at a point. Let me call that point Q. So that point Q represents the system of stresses on a plane inclined at an angle theta with the major principal plane. So on the plane inclined at an angle theta, I have the system of stresses sigma and tau, just what we saw on the wedge ABC earlier, correct? Wedge ABC, angle BAC was theta. I represent that angle here. I join the point P, and I'm from the point P, I draw a line inclined at that angle BAC theta. So that line will join the point Q here, and that point Q, the coordinates sigma and tau are the normal and shear stresses acting on the plane AB, which was inclined at theta to the major principal plane, correct? Now, so similarly, on any plane that is inclined at any angle to the major principal plane, I can draw similar planes or subtend similar angles from the point P, and I can draw any plane here, and those planes are going to intersect on the Mohr circle at different points. Those points as coordinates represents the normal and shear stress on that particular plane which is inclined at any of that angle that it makes with the pole. So this coordinate, how do you find out this coordinates? So you just find out this. This is my sigma and this is my tau, because this angle represents normal stress. So now, so how do you find the coordinate for this particular thing from the graph? Is the sigma is nothing but OE, right? So OE is equal to OF plus FE, right? So OF is nothing but sigma 1 plus sigma 3 by 2, right? Suppose sigma 1 is 100, sigma 3 is 50, 100 plus 50 by 2, 75, correct? OF is 75, isn't it? Now I have to find out FE, right? FE, consider this theta. Consider this 2 theta. As you can see here, consider this QFE. Now consider this 2 theta. So now I have FE is equal to sigma 1 minus sigma 3 by 2, where sigma 1 minus sigma 3 by 2 is the radius of the circle, FQ. So sigma 1 minus sigma 3 by 2 sine 2 theta, I will get this distance FE. So OF plus FE will give you your this distance OE sigma. So I got my sigma there. Then tau is equal to this distance. Again, from the same triangle, I can find out my tau, which is sigma 1 minus sigma 3 by 2 into sine 2 theta, right? This distance. So I can similarly, I can plot any plane inclined at any angle theta from the point P or the pole inclined at any angle to the major principal plane, and the point where it intersects on the Mohr circle, I can find out the coordinates like this, which will represent the normal stress and shear stress on that particular plane inclined at any angle. Yeah, from P, a line PQ is drawn parallel to the plane of AB as shown here at an angle theta to PD. Right, this is my major principal plane here. So coordinates of point Q on the Mohr circle represents the normal and shear stress on the plane AB, sigma and tau. So here the plane AB is arbitrarily chosen. So we can say that any line drawn through the point P parallel to any arbitrary chosen plane intersects the Mohr circle at a point. So that point's coordinates represents your normal and shear stresses on that plane. This is what we just discussed. So any line, a line drawn from any point on the Mohr circle. Now we are going to do it ulta, right? Suppose we have the point Q. Okay, earlier we from the point P we found out that we knew that angle theta and we drew that line. Now imagine any point on this Mohr circle. Suppose let us say Q. So from that point Q, if I draw a line to the pole, okay, how did I get Q? Suppose I know the normal and shear stresses acting on the soil element, okay, or on the soil wedge. I know the sigma and tau. So I'll find out the coordinates of sigma and tau on this Mohr circle, and I'll plot that particular point Q. Let me call it Q as of now. Then what I will do is from the point Q, I will draw a line that passes through the point P or the pole. Now that line will make an angle theta with the major principal plane, and this system of stresses, this sigma and tau will be acting. You can say that this sigma and tau will be acting on a plane which is inclined at theta. Suppose you didn't know the theta initially and you knew only the normal and shear stresses. So you can do this in the backwards also. Right, so sigma and tau you will mark from that particular point. You will draw a line that passes through the pole. Now if you find out the angle that particular line makes with the major principal plane, you can say that okay, my system of stresses sigma and tau are acting on a plane which is inclined at theta to the major principal plane. All right, so this unique point P is called the origin of planes or the pole. Okay, now another thing I want you to understand is that this major principal plane here OX, for this will be the simplest problem you can get, because in this case the major principal plane OX is like this. It is not inclined. Okay, sometimes the major principal plane can be inclined. Alright, the major principal plane need not always be along the x-axis, correct? The major principal stresses within a soil element can act in any plane. Okay, the plane can be inclined. It need not be along the x-axis. All right, so keep this in mind. So as of now, this is the simplest problem you can get here because your OX is your major principal plane. Sometimes your major principal plane will be like this. Sometimes the major principal plane is suppose something like this. So in that case, this will be my pole. Okay. So from this plane, I can draw the line PQ or any line inclined at an angle theta to the major principal plane. So in this case, it is very simple, very easy to visualize. That's why I took the simplest problem here. So here your major principal plane is along your x-axis. Very simple problem. So keep in mind that it can be inclined at any angle for different soil conditions or cases that you're going to see later. Okay. So it can be anywhere inclined. It can be in any direction. It can be anywhere. Okay. It can be anywhere. It can even be vertical. So you have to identify your major principal plane, then plot that plane on your Mohr circle. All right. Then identify your pole. From your pole, if you draw any line, it will pass through. It will intersect the Mohr circle at some point, and that coordinates will give you your normal and shear stresses at any plane inclined at an angle theta to the major principal plane that you have just constructed. Now look at this Mohr circle here. So from this, a few other relations can be drawn. So where will be the maximum possible shear stresses? Here the line PQ we drew, and this is my tau shear stresses on that plane AB, which was inclined at angle theta, right? This one. Okay, so now if you look at this Mohr circle, where can be the maximum shear stresses? This was a shear stress on that plane AB. So where can be the maximum shear stress? Obviously, it will be the maximum will be at the radius of the circle, right? So you can see tau max here, right? I have constructed the tau max here. Can you see the tau max? Right, this is the tau max. Okay, so that will happen when this angle here. So on which plane will be your tau max? So what you have to do is you have to, from this point, what you will do, you will draw a line which passes through the pole, correct? To find out on which plane it acts. So tau max is my maximum shear stress possible. So I will, from this particular point, I will draw a line which passes through the pole and find out this angle. So if I do that, I can see that this angle is 45 degree, obviously, isn't it? So tau max will occur on a plane inclined at an angle 45 degrees to the principal planes, right? Which is very obvious from this Mohr circle figure, right? Now, so tau max, I can say that tau max is nothing but radius of the Mohr circle, which is sigma 1 minus sigma 3 by 2. Suppose sigma 1 was 100, sigma 3 is 50. It is 100 minus 50 by 2, which is 25, which is nothing but the radius of the Mohr circle. So that is my tau max. I got my tau max at this point. What I do is I subtend an angle here. I draw a line here which passes through the pole. I find out this angle, so I know on which particular plane or what is the inclination of that plane with the major principal plane on which this tau is tau max. So now I found that it is 45 degrees. Clear? And the normal stresses on the plane of maximum shear stress is half of sum of principal stresses. So what will be your OF? So on that particular plane on which your shear stresses are maximum, so this is the plane. On that plane, your shear stress is maximum, tau max. On that plane, what is your normal stress? This one, OF. So how much is that? It is half of your sum of principal stresses. That is 100 plus 100 plus 50 by 2. Correct? 75, isn't it? OF. Right? Hope we are clear there. So I found out where I will have my maximum shear stresses. So it will be on a plane inclined at 45 degrees. So, and sigma C will be sigma 1 plus sigma 3 by 2, that is OF, right? Now the resultant acting on that plane, or let me say any plane. Do you remember this figure? So the resultant acting on that plane AB inclined at an angle theta to the horizontal, you can see I had my normal stress sigma, I had my shear stress tau. So this was my resultant. So how do you find out this resultant? Very simple equation. That resultant will be root of sigma square plus tau square, right? We have seen that. And this beta is my angle of obliquity. How much will be that beta? Again, very simple, tan inverse of tau by sigma. Correct? Consider this triangle. So beta is equal to tan inverse of tau by sigma. So I can find out my angle of obliquity as well. So where will you have maximum obliquity? So this here, you can, as you can see here, this here, let us go back to this plane AB, which was inclined at an angle theta. So that theta is here. PQ is the plane that represent plane AB. So PQ. So this, if you subtend it back to the origin, you will get that angle of obliquity beta, because this represents your sigma, this represents your tau. It's just similar to this, isn't it? This represents your sigma, this represents your tau, and this angle is your beta. Just similarly, this represents your sigma, this represents your tau, and this represents your beta. And this line represents this resultant stress, isn't it? So this actual condition, I had recreated it using a graphical method using a Mohr circle. Now if you look carefully, you can see this OE is this one, right? And EQ is this one or this one in this triangle somewhere here, and this OQ is my resultant. This angle subtended is nothing but beta. So where can you have a beta max? Okay, where will you have your beta max? So how do you find that? So the maximum angle of obliquity, beta max, it occurs on a plane of angle theta critical tau, which is represented by this blue line, which is represented by this blue angle. All right, angle theta c tau represented by this blue line with respect to the major principal plane. All right, this one, and I subtend that angle, or this is my beta max. That beta max is the tangent on this circle. As you can see here, is a tangent on this circle. Okay, because this will be the point where you will have your maximum possible sigma and tau here, right? Combination of those. So I have this line. So from that point of intersection, if I join it back to P, I will have my theta c tau, which is nothing but 45 plus beta max by 2, this angle. All right, so if I know this point, I subtend it back to point P. So I have that angle, this angle 45 plus beta max by 2. So this is my beta max, the tangent that touches the Mohr circle from the origin. So there I have my beta max. All right, so this angle is 45 plus beta max by 2. So the maximum angle of obliquity can be obtained by drawing the line which passes through the origin and tangential to the Mohr circle. So subtend it back, you will have your theta ct shown by this blue line and this blue angle. So that will be your maximum angle of obliquity. Now, keeping these things in mind, okay, now we are clear with the resultant angle of obliquity beta, maximum possible obliquity angle, then the plane at which the plane AB is inclined to the major principal plane theta, then what is tau max and what is sigma and what is tau. I think we are very clear with this, the graphical representation of it and resolution of this wedge. I think we are very clear with it now, right? So keeping these things in mind, let us move to our topic, shear strength theories for soils. Okay, so the most simple or the most basic or the first theory that was proposed for the shear strength of soil was the Mohr's strength theory. Okay, the Mohr's strength theory. Now what we follow is the Mohr-Coulomb strength theory, which is a modified version of this Mohr strength theory. So to understand that, you need to understand this. All right, so let's go. Yeah. So Mohr strength theory, it is based on a few assumptions. So first assumption is that the ultimate strength of a material is determined by the stresses in the plane of slip. All right, I told you earlier, no chain is stronger than its weakest link. Right, there will be any point of weakness or a plane at which the soil can fail. Suppose you look at the bottom right figure, you can see a retaining wall here, you can see this failure surface. Right, I was applying a load here, or due to the self weight of the soil here, some normal stresses were acting on the soil, and slowly it failed and it got displaced along a particular plane as shown here. All right. So the ultimate strength of the material is determined by the stresses in this plane of slip. Right? The soil is going to fail along that particular plane on which there are a system of stresses. So the maximum stresses the soil can bear will be the stresses on that failure surface. That is my first assumption. Second one, the failure of a material is essentially by shear. But the critical shear stress is governed by the normal stress on the potential failure plane and the properties of the material. So this one, let me take you back to your basic physics, what you learned in your school. So see here, I'm trying very hard to push this block. Okay, so there is some normal stress acting on it, and there is some frictional force that is acting against my push here. All right, so the frictional, so if I need to move this block, I should surpass the friction developed at this plane, right? Yeah, I need to surpass the total friction developed at this plane. So how will you calculate this total frictional force developed on this plane? A simple equation, F is equal to mu into N, where mu is my coefficient of friction. Right, there is some friction between these two surfaces, so that coefficient of friction is dependent upon many parameters, like the angularity of the surface, how rough the surface is, etc. Right, I mean, in the case of soil also, you can relate it to how angular your soil particles are, right, or how lubricated your soil particles are, right? So this plane, some frictional force will be developed, and that is a function of the coefficient of friction multiplied by the normal force. So if I increase this normal force, maybe I can easily push this block, but if 5 of you guys sit on this block, it will be more difficult for me to push this sideways. Why? Because there is some normal force acting on it downwards, and the coefficient of friction hasn't changed, but your normal force has changed, so it will become very difficult for me to push it. Right, so basically what happens in the soil here is, you can see here, or here you can see, I'm trying to push the soil down, right, but along this plane the soil has some frictional resistance and it tries to hold its place, right? Just like I am trying to push this, the soil, due to its self weight, it is trying to push it down and displace the retaining wall. But there is some friction developed along this plane which prevents this particular movement. So if I increase the normal stress on it, I keep on increasing the normal stress on it, it will become a bit more difficult for me to push it down, isn't it? Why? Because my frictional forces generated will also increase. Correct? Like 5 guys are sitting over here, I try to push it, I need to push it more, but the resistance developed on this plane, F is equal to mu into N, will be more. Why? Because the particles can interlock better if you apply more normal stress, isn't it? Can you visualize a few soil particles? Try to visualize a few soil particles loosely packed, and you're trying to roll those particles over each other. It's very easy, isn't it? But now imagine there is some normal force acting on that particle. So what will happen? The particles will come together, isn't it? The particles will come together, interlock better, more surface on which the friction is mobilized. So what will happen? The particles interlock better. Now if you try to roll the particles over each other, you have to apply more force to overcome the friction developed, isn't it? So what caused it? The normal force that you apply, correct? So if you apply a higher normal stress on the potential failure plane, then you will have to uh, apply more shear stresses to overcome it, right? So the failure of the material is essentially by shear, but the critical shear stress is governed by the normal stress on the potential failure plane. Not only that, and also the properties of the material, like the coefficient of this friction. Clear? Now, in a three-dimensional stress system, the magnitude of the intermediate principal stress has no effect on the strength of the material. That is sigma 2. We are going to neglect sigma 2 from here onwards. So we will consider sigma 1 and sigma 3 major and minor principal stresses. Okay. So this is Mohr's strength theory. Let us see. So on any plane, the shear stress tau. So now let us see, let us construct another Mohr circle here. I have my plane OX and OY. OX represents my major principal plane here. OY represents my tau here. So OX represents my normal stresses, OY represents my shear stresses. I constructed a Mohr circle based on my maximum and minimum, or the major and minor principal stresses. I am disregarding my sigma 2. So sigma 1, sigma 3 I plotted, I drew my Mohr circle, I found out the center, I drew the Mohr circle based on the radius that I obtained from this. Now I have my Mohr circle. Now on any plane, the shear stress tau, it is given by tau is equal to sigma tan B. Now imagine, you can see here, let us imagine OQE. Okay, let us look at OQE. Okay. So look at this figure, OQE. I know where my tau is, I know where my beta is, I know where my sigma is. Right? So I can say that this tau is equal to sigma tan beta from this figure, isn't it? Can you see this? Correct? I can say that tau is equal to sigma tan beta. Correct? Yeah. I can say that my tau is equal to sigma tan beta, and for any given stress condition, for a given stress condition, that beta will attain a value beta max on the plane PQ. You can see the plane PQ here. So how will I find out this beta max? We saw earlier, how will you find out this beta max? You will draw a line from the origin. You will draw a tangent to the Mohr circle, right? You will draw a tangent to the Mohr circle. So that angle will be your beta max, maximum angle of obliquity, right? This is the maximum angle of obliquity you can draw for this Mohr circle, isn't it? The angle that is subtended by that sigma and tau. So this is the maximum beta you can draw for any Mohr circle. Suppose this is my Mohr circle, limiting circle at failure, the second one. This is my Mohr circle. So for any Mohr circle, the maximum beta max you can draw is the tangent from origin. Correct? So this beta max I drew. Now this system of stresses at Q, I know my sigma and tau at point Q if I find out my coordinates of point Q. Correct? If I find out this sigma and this tau, I will find out my Q. Correct? And how will I find out this sigma and tau? I can find it directly from this graph, or I can find out this distance, and I can find out this distance, and this relationship will be this one. Tau is equal to sigma tan beta max here, isn't it? That will be the relation. Correct? So for a given stress condition, this beta will attain beta max on this particular tangent, right? And if I subtend from this particular point Q, if I subtend a line to the pole, what will I get? I will get the failure angle. I mean, I will get the angle at which that particular plane is inclined with the major principal plane. Here OX is my major principal plane. I find out the coordinates of the point Q. From that point Q, I'll draw a line to point P. Now, if I find out the angle that line QP is making with the major principal plane, what will that angle represent? Theta F. That angle will represent the inclination of the plane with the major principal axis on which the system of stresses sigma and tau are acting. Correct? Now I find out this tau F. That tau F is my failure angle theta. Okay, that is the maximum possible beta max. This is the maximum possible beta. So in that soil, the maximum possible is this sigma and tau, right? Now, so if you are considering a cohesionless soil, you are considering sandy soil, suppose let us say you are considering sandy soil. So this beta max will be equal to phi, which I call the angle of internal friction, which is one of the strength criteria for soil. So soil gets its strength from two parameters we discussed in the first class, which are one is the friction between the particles and the other one is the cohesion between the particles, right? Do you remember? And how does they get their friction? Due to interlocking or friction developed against rolling or sliding between the particles. And the other strength parameter was cohesion, which is developed due to the electrostatic forces between the particles. So suppose you are imagining a cohesionless soil, which is sandy soil. They do not have any electrostatic forces acting between them. There is no cohesion. So where do they get its strength from? You get your strength from phi. That is the friction between the particles. So the maximum possible beta max here represents the maximum no the plane the angle of obliquity of uh, the resultant where maximum sigma and tau or the failure sigma and tau is possible is represented by the angle of obliquity beta max, and that plane at which it is inclined is theta f. So this beta max will be equal to phi, which where the phi is the angle of internal friction of the soil, right? So shear stresses on that failure plane. So now my failure plane is PQ. As you can see here, the failure plane is inclined at an angle theta f. It makes angle beta max, the maximum obliquity angle beta max. And what will be the equation of this line? What will be the equation of this line, or what will be the how will you find out this tau f? That tau f will be equal to sigma f into tan beta max or tan phi, isn't it? You consider this Q, O and this particular point here. Suppose you imagine a triangle here, right? So this will give you your tau f. All right, this will give you your tau f. This will give you your sigma f, and this angle that it subtends will give you your beta max or phi. So what will be the equation for this line? It will be sigma f tan phi, isn't it? See this line, correct? So for every sigma f, for every sigma along this line, if you multiply it with tan betas, you will get a point tau 1, sigma 1. Suppose till this distance sigma 1 or sigma a, as there is another sigma 1, I am going to take sigma a. Suppose till here it is sigma a. Multiply it with that particular angle phi. I will find out my tau a. Then another point sigma b, tau b, sigma c, tau c, sigma d, tau d, sigma e, tau e, right? So if I join all those points, I can again I'll get the same line, correct? I'll get the same line. And what will be the equation of this line? It will be tau f is equal to sigma f tan phi, isn't it? Correct? So sigma f is the normal stress on that failure plane. So this is the line that represents the inclination of that failure plane. It is inclined at theta f to the major principal plane. So the limiting value of shear stress, that limiting value of shear stress that you get along this plane is called the shear strength of soil, right? That maximum limiting stress value will be the strength of the soil, isn't it? The maximum shear stresses the soil can bear will be termed as the shear strength of the soil, right? So this limiting values of shear stresses for different normal stresses is represented by this line OA, tau f is equal to sigma f tan phi. So those values are called my shear strength of the soil for different normal stresses. So for this particular Mohr circle, For this particular stress systems, my limiting shear stress. So for a soil with a normal stress sigma f and tau f, it will be inclined at an angle beta max, which is equal to phi. For this Mohr circle, my shear strength of the soil will be the limiting value of shear stress. This tau f. This tau f will be my limiting value of shear stresses in the soil, which is basically my shear strength. Correct? The limiting value of shear stress in the soil is its shear strength. So what is that limiting value of shear stress here? Tau f. So that tau f will be my shear strength of my soil. Right? So for a cohesionless soil, I can say that the shear strength is S. Strength is equal to limiting value of shear stress tau f, which is represented by sigma f into tan phi. Correct? This tau f will be my strength of the soil for that given sigma f. Correct? So now if I increase my sigma f, suppose this is my sigma, I increase the normal stress. So what will happen? My coefficient of friction or phi, angle of internal friction of the soil, it is not going to change. So my limiting shear stress is going to increase here. Correct? So tau for this sigma f, I will get this tau f. Correct? So if I keep on increasing my normal stresses, this is the general trend it is going to follow. But the catch here is that if you keep on increasing your normal stress, do you think the shear strength of soil or the shear stresses that can be induced in soil will also exponentially keep on going up? No, right? There will be some limiting value for that, isn't it? So this line will not always be straight. After a point, it can flatten out. Okay, we will discuss that later. Do not have an impression that this line will keep on going infinitely, and for an infinite normal stress, you will have infinite shear stress developed in that soil, and that is the strength of the soil. No. Okay, so this will change. This will limit at some point, particular point. But what is the constant parameter in that? That is your phi, that coefficient of friction. So that is considered as one of the strength parameters of the soil. So phi, which is my angle of internal friction. So cohesive soils, where do they get their strength from? Due to the friction against sliding or rolling over of the particles and due to interlocking between the particles. So that is how you get your phi. I hope it is clear. So now, if the angle of internal friction is assumed constant, let us say it is phi. I'm keeping this constant. So the equation is represented by the straight line OA, right? That is how I got, tau f is equal to sigma tan phi, correct? So that line gives the relationship between normal stress and shear stress at failure. And this particular plane, this plane represents the failure envelope. So along this particular line, okay, throughout this line, I have the maximum possible shear stresses for any of the normal stresses I consider. For this normal stress, this is the maximum shear stress. For this normal stress, this is the maximum. This normal stress, this is the maximum. So this particular line represents the maximum possible combinations of sigma and tau for a given angle of internal friction. Correct? So this line, I call it as the failure envelope or Mohr's strength envelope. Okay, it can be straight or curved. As I mentioned earlier, it can get curved. Okay, it can go curved. So that depends upon the soil properties. We will see that later. Okay, so as this failure envelope OA defines the shear stress at failure, tau f is equal to sigma tan phi, sigma f tan phi, shear stress at failure as a function of normal stress. So failure can occur only when a Mohr circle for a stress system touches this failure envelope, isn't it? Suppose my stress system is represented by this circle 1. I have sigma 1 here, I have sigma 3 here, and this is my Mohr circle. And the maximum possible sigma and tau combinations is beta max, which is represented by this failure envelope. Unless and until my stress systems go on increasing and touch this Mohr circle, my soil is safe, or it is not undergoing any failure. The failure plane might not even be developed. So you can see for the circle 1, okay, can you see the circle 1? This is my circle 1. Okay, so in none of the points or none of the coordinates of circle 1, I am going to a point where my stresses are sigma f and tau f, because sigma f and tau f all lies along this line, correct? Where is my beta max? So beta max is phi. So tau f is equal to sigma tan phi, correct? So nowhere along this circle 1 I am touching my sigma f or tau f, or even this line that represents those combinations OA. So I can say that my circle 1 is safe, correct? Now imagine circle 2. So look at circle 2. So this is my limiting circle at failure. Why? Because this circle touches this failure envelope at point Q, isn't it? So this line OA represents my sigma f and tau f combinations for a constant phi. So this circle is going to touch this point at point Q, correct? Sigma f and tau f is achieved. So the soil with this stress systems, it will generate a failure plane which is inclined at an angle theta f. So this circle I will call my limiting circle at failure. Now imagine the circle 3. Is it possible to have a circle 3? Because the stress systems go way above this failure envelope. So if you are considering this point where my mouse is pointing right now, you will calculate a sigma and tau at this particular point where my mouse is pointing right now. Is it possible for a soil with angle of internal friction phi to have a stress system sigma and tau at this point? It is not, isn't it? Because your maximum possible sigma and tau are along this line. So it is impossible to have a condition like this. Or you can say that if you keep on increasing your stresses like that, it will fail at this point before it even reaches any of these points, correct? Isn't it? So the stress systems, the combination sigma and tau along this particular line, until by the time it reaches here at this point, as you can see, by the time it reaches here, the soil will fail. It will not even reach these levels of sigma and tau. Correct? Before that, it will fail here. If you increase your normal stress till here, if you increase your normal stress till here, your shear stresses induced will be this much. And above that, if you further increase your sigma, it is going to fail at this point. Correct? So this circle 3, it is very difficult or impossible to have this circle 3. So the limiting circle at failure here is circle 2. So I can now say that this is my failure envelope for a purely cohesionless soil which is having its angle of internal friction phi. I can say that this is my failure envelope or Mohr's strength envelope, and any stress systems or stress combinations within the soil within or equal to this limiting circle at failure, the soil is going to be safe against shear failure. A stress system above that, my soil is going to fail in shear. Anything within this limiting circle at failure, any stress systems within that, my soil is going to be safe. This I can observe visually. So if I know a angle of internal friction of the soil, I can construct this stress system and I can draw the failure envelope. And for any sigma 1 and sigma 3, if I draw a Mohr circle, I can say that whether that soil is going to withstand that levels of normal stresses or not. That is pretty much obvious from these Mohr circles that you are going to develop. So no failure occurs for circle 1. It is not possible to have a stress condition represented by circle 3, as the soil would have already failed prior to such stresses. At this point itself it will fail, and circle 2 is known as the limiting circle corresponding to failure. So this is how Otto Mohr used the Mohr circle for understanding this, and this is how you can use it to identify what will be the failure envelope and the maximum possible shear stress and normal stress combinations for a particular soil having a angle of internal friction beta max or represented by phi. I hope it is clear. So from this figure again, you can find out this angle theta f, which is nothing but 45 plus phi by 2. We saw that earlier. Theta f is equal to 45 plus beta max by 2. We saw that in the earlier figures. So this angle theta f, you can actually find out at what angle your soil is going to fail. You can find out the orientation of the failure plane PQ. This PQ represents your orientation of the failure plane, just like you saw angle BAC in that failure wedge. Theta was the angle at which plane AB was inclined to the major principal plane. So here you can see PQ is inclined at angle theta F. All right, and at Q you can see that the soil fails, right? That is your limiting values, correct? So you can find out at what angle your soil will fail. All right, what angle will your failure plane be? Theta F. So that will be equal to 45 plus phi beta max by 2, or 45 plus phi by 2. That will be your theta F. Just the same thing that we saw in the previous figure. All right. Also, another relations can also be derived for that theta F. Your sigma F you can derive from this figure, and this tau F and sigma F you can derive from this figure, which shows sigma F is equal to sigma 1 minus sigma 3 by 2 cos square phi by sine phi, and tau F is equal to sigma 1 minus sigma 3 by 2 cos phi. So you can find out the relations for this, and you can if you know the angle of internal friction of the soil, you can easily develop this failure envelope, and you can draw the limiting circle and failure. So for any system of stresses, you can develop these, and you can identify whether your soil is going to fail or not, and you can also identify all the different planes on which different system of stresses act within the soil using this. I hope the Mohr circle and its construction and its application is clear.